In this video, we're going to talk about how to apply Newton's second law for a system with multiple objects. And very often what's going to happen in that system is there's going to be some things that have linear motion, and then there's going to be some things that have rotational motion. And so you're going to have to use Newton's second law for linear motion, sum of forces equals ma, for part of it, and then Newton's second law for rotation, sum of torques equals I alpha, for the rotating objects. So a good example is the one that I'm working through, that I'm going to work through here, that I have illustrated here, where I have a level surface, level frictionless surface over here. So I'll write here that there's no friction on this surface, and then it connects to a ramp that has friction, and then at the edge of that little join, there's a pulley, and the pulley does have mass now. So we might have solved this sort of problem, but when we ignored the pulley. So what do we do now if we don't ignore the pulley anymore? And this whole thing is then accelerating as I've indicated in that direction. So that's going to be our three-body problem. So the first thing that you're going to do in these problems is to count the number of objects that have mass. In this case, I have M1 and M2 and the pulley. That's three objects. That means in order to solve this, I need to write three equations of motion. Now, then you need to figure out which ones are accelerating linearly, which one's center of masses are going to be, moving, just linearly, like we're used to with sum of force equals ma, and which ones are pivoted, which ones are going to be rotating, and that's going to use sum of torques equals I alpha. So to write those equations of motion, we're going to do the same thing we've always done for each one, but now it's going to combine into one problem-solving technique. So the main thing here is that let's go ahead and summarize what I said, and then we'll go ahead and we'll start with the linear objects, and then we'll move on to the rotating object, and then we'll see where we go from it. All right, so note a key idea is that you will have an equation of motion for each object when you're done with this. So when you're done, you're going to have an equation for each object. For objects with linear motion, you're going to use Newton's second law for linear motion. You're going to use the sum of forces is equal to ma to get those equations of motion. And for objects that are rotating, then you're going to use Newton's second law for rotational motion. So that's it. And then at the end, we're going to see how we can relate those three equations together to actually solve, our problem, because one will be in terms of the angular acceleration alpha, and others will be in terms of a linear acceleration of the center of mass, a. Okay, so that's the overall goal. And so what I'm going to do here is let's go ahead and start with the linear motion. So there aren't really new steps here. It's the same steps to write the equations of motion. So I'm really just by example going to work through this problem. There's also the annotated worked example on this as well that you can follow through. So I'm going to start here looking at M1. So M1, the box on the no friction, is going to be having linear motion, and the tension force is acting on it. Right? So I'm going to have to draw a free body diagram, and I'm going to have to label that tension. Now remember, this is really critical, that the tension now in our continuous rope that's shown here is no longer equal on both sides of the pulley, because if the two tensions are equal, then that pulley can't turn, and we need the pulley to turn, right? The pulley does need to rotate, and in this case, the angular acceleration would need to be into the page. For that, for that acceleration downward. And so what's going to happen then is that means that I'm going to have two different tensions. So I'm going to go ahead here and I'm going to label this tension up here T1, And then just so we have it for later, the tension in this portion of the rope, I'll label that T2. So you're gonna have to divide up the tensions in a rope that way. It's no longer just a single tension. So I'm gonna start with linear motion. I'm gonna look at this M1 over here. So let me go ahead and I'll do it in purple because it's drawn in purple in the diagram. And so this would be M1. It's on a table, so it's gonna have a normal force upward. It's going to have M1G down. Now, because I don't have friction on M1, I don't really care about the normal force, but we can see that it would be equal to M1G because I don't have any other up or down forces besides M1G. And then I just have the tension. So this is actually a very simple Newton's second law one. And so remember with Newton's second law with linear motion, we want to draw the direction of the acceleration and I want to define an axis. And so once I do that, then I'm able to kind of write out very nicely my equation of motion. My sum of my individual forces in the x direction is simply T1, just one force, that's okay. And then step 3, set it equal to plus or minus ma. I can see the acceleration is in the positive x direction. And so I'm going to set that equal to positive, and then I have to keep my subscripts here, m1 times a. And that's going to be the linear acceleration of the system. Remember, the whole system has the same linear acceleration. So I'm going to box that, mark it, and that's going to be my equation of motion for m1. So equation of motion for m1. Great. So then I look to see if I have any other objects rotating. Sometimes you just have one, sometimes you have multiple ones. I do. I have blue M2. So let's go ahead and draw M2. And I made M2 a little bit more complex just to bring back Newton's second law, some of the things that we've been, haven't been working on since we've been in rotational world. So this is going to be M2. I'm going to have a normal force perpendicular to my ramp. I'm going to have M2G downward. And then I have the fact that it's going to be sliding down the ramp means that I'm going to have two forces up the ramp. I'm going to have the tension force. So I'm going to kind of just draw that here. That's going to be T2. Again, that's other component of the tension. And then with the floor, I'm going to have my friction force because there was friction in the problem. And again, I want to draw in my acceleration and my coordinate system. So because I have friction, I do have to get the normal force from my sum of forces in y. So this is kind of just a quick recap. Hopefully it's very familiar. So get this normal force from the sum of forces in y. So from the sum of forces in y, I see that I have n minus m2g cosine theta. That again, as a reminder, comes from the components of a ramp. I'd refer you back to that material if that was not a straightforward step at this point. N minus m2g cosine theta equals 0 because it's not accelerating in the y direction. So n equals m2g cosine theta. Great. And so then remember that f sub k equals mu sub kn. So f sub k equals mu sub k m2g cosine theta. All right, so now I'm ready to actually write out my equation of motion for this in the x direction. So the sum of forces in x is going to give me here, I only have one component of a force along the x direction, right, in the positive x direction. And that's going to be the component of the weight down the ramp. So I'm going to have positive m2g sine theta. So that's this component of the weight down the ramp. A lot of people forget about that one, but don't forget about it because it's literally what's making it slide down the ramp in the first place. So m2g sine theta minus T2 minus this f sub k. So minus mu sub k m2g cosine theta. And then I have to set that equal, the sum of the individual forces, set it equal to either plus ma or minus ma. And in this case, I also have a in my positive x direction. So I'm going to set that equal to plus, and then remember your subscripts, m2a. I'm going to give that a nice box. mark it so it's easy to find, and we are set. So I now have my two equations of motion for my two linearly accelerating objects. So I'm 2/3 of the way there. If we go back to the original problem, I still have this motion of my pulley. We are not ignoring the pulley anymore. If we were ignoring the pulley, then T1 would equal T2, and we would have our system of two equations. But now we're adding in the complexity of the pulley. So let's go ahead now and see what we're going to do for the pulley. So for the rotating objects, I follow the steps that we just learned about applying Newton's second law to a single object that's rotating. So for rotating objects, in this case, the pulley, I'm going to use the sum of torques is equal to I alpha. So I'm going to have to then draw my extended free body diagram of the pulley. So there's my pulley. I was told in the original problem that it has some radius r and some mass m sub p and a radius r. And let's assume, it'll tell you in the problem, assume that we can model it as a solid disk. The problem will always tell you what to assume about the makeup of a pulley. If you can assume you can model it as a solid disk, what that means is that the I would be that of a solid disk, which is just equal to 1/2 mr squared, so m sub p r squared. So we do know the moment of inertia for that pulley from our table. Okay, so what forces are acting on it? If we look at this diagram, you can see that the only things acting on a pulley are tensions. The weights of other objects don't act directly on the pulley. That acts on the other objects. The only thing that acts on pulleys are tensions. Ropes pull on pulleys. And so I'm going to have here tensions point away from the object along the rope. This is going to be T1 here. Again, away from the object along the rope. If you were the pulley, which way would those ropes be pulling you? And that would be T2. We know that this whole thing is accelerating as I've shown here. So in terms of thinking about alpha, I would do my right-hand rule and I would realize that alpha is in the negative z direction. Some people prefer to think about that as into the page. So alpha is in the negative z direction in this case. Okay, and so what that's going to allow us to do is write out our sum of our individual torques. So our sum of our individual torques, and we only do this along one dimension because we just have a single axis that we deal with for our rotational type problems along that axis that the pulley is spinning on. So the sum of torques is going to be coming from R cross F. So remember then that R points from the axis to where the force is applied, and it's always going to be perpendicular. So in this case, I can write out the sum of the individual torques. If I look at the direction of them, let's start with T1. So T1 would be here. I would have the magnitude of that R, so I'm going to use R cross F. Magnitude of R is just capital R times the magnitude of the tension, T1, and then times the sine of the angle between them, so sine of 90, and then I have to decide if it's plus or minus. And so for this one here, I can see that it's out of the page, so that's going to be plus, and so that'll be plus z hat. And then minus, and that's going to be because if we look at the T2 torque, I'm going to have R cross T2. It will be into the page, so there'll be minus R T2 sine of 90 z hat, because it's an opposing torque. And it's actually in the direction of our angular acceleration, even though it's negative, but that's okay. So that's going to be my left-hand side, right, of our Newton's second law of rotation. And then I'm going to set it equal to minus I alpha, because alpha is into the page. So then I'm going to end up with my equation of motion, and I'm going to write it down here because I'm also to take into account the moment of inertia. So RT1, sine of 90, that's just 1, so I'm going to leave it out, minus RT2, sine of 90, again, equal to 1, so I'm going to leave it out, equals, and then negative I, so 1/2 m sub p r squared alpha. And at this point, I've done all I can do for writing my equation of motion. I'm going to box it and keep it. And so now I have my 3 equations of motion. So this is my equation of motion for the pulley. So I now have my 3 equations. At this point, you might think, great, I'm done. It's just algebra. But there is one more step, and this step is very important. So at this point, now decide if you want alpha or A. So you have to decide whether or not the problem's asking you, I mean, really just look at the problem. Is it asking for you the angular acceleration or the tangential acceleration? The linear acceleration of the whole system. Either way. And then what you're going to do is you're going to use alpha equals A sub t over r. And that's then just going to be equal A sub t. The tangential acceleration of the pulley is the linear acceleration of the system in most cases. Once you know what that r is, right, is going to be equal to A, and in this case, because it's on the outside of the pulley, over r. So to sub into your equations to eliminate either alpha or A. So this is an exceptionally important result that makes it so that you can also solve your system of equations. So in this case, for example, say that we want the linear acceleration. Then what I'm going to do is rewrite the pulley equation. And it'll say then RT1, and I'll rewrite it in red actually, just so we can keep track. So RT1 minus RT2 equals negative 1/2 m sub p r squared times alpha, but now I'm going to just put in A over r. So now I have an equation that has A in it. So it has T1, I have 3 equations and 3 unknowns. So now I have 3 equations and 3 unknowns. My 3 unknowns are T1, T2, and my acceleration of my system. So at this point, I just need to solve those. If you're very comfortable solving them and eliminating T1, T2, and A in this system of equations, then at this point, you can be done with this video. If you'd like to see me work through that, you can. It's also worked through in the annotated worked example in a lot of detail, as well as the guided tutorial. All right, so what I'm going to do then is rewrite my first 2 equations from up here, just so I have them all in one space. So I'm basically just going to have these 2 equations here, T1 equals M1A. So I'm going to have T1 equals M1A. That one was easy. And then I'm going to have this one here, which is what I've shown. And so that's going to be M2G sine theta minus T2 minus mu sub K M2G cosine theta equals, and it equaled positive, that's right, it equaled positive M2A. And then lastly, I have this equation here, and I'm actually going to simplify this a little bit. You can see on this equation that I have r squared over r, so that turns into just 1r on that side. And I have an r on this side. So my r actually goes away from this equation, which is great. And so then I can write this as T1 minus T2 equals negative 1/2 m sub p times a. So that's actually my Pauli equation, just by canceling out all those r's once I substitute in for a. So those are my three equations and my three unknowns. What I'd want to do is solve it, and by eliminating T1, T2, and then say solve for a. So there's a lot of different ways for solving these equations. One way is to just solve your linear equations. Put T1 equals and then T2 equals and then plug it into your Pauli equation. So that's what I'm going to do. This one is already written in that format. And so I'm going to then rewrite the second one as T2 equals. So I'm going to move it over to that right-hand side and then move M2A over to the left-hand side. So T2 would equal M2G sine theta minus mu sub k M2G cosine theta, and then minus M2A. So now I have these two, and then they can be plugged into the Pauli equation. This last one here, this T1 minus T2. So I'm going to have T1, that's M1A from this first equation for T1. And then I'm going to have minus T2, which I'm going to plug in this whole thing. So that one's going to get a little bit messy. So minus T2. So I'm going to make every term there opposite signs. Minus M2G sine theta, and then plus mu sub k M2G cosine theta, and then plus M2A. So that's T1 minus T2, and then equals negative 1/2 m sub p a. Okay, so at this point, I need to solve this for a, and a shows up in 3 terms. So what I want to do is I want to move all those terms to the left-hand side and move all the other terms to the right-hand side. So I'm going to write this as M1A plus M2A plus, because I'm moving it over, 1/2 m sub PA equals, and then moving everything to the other side, M2G sine theta minus mu sub K M2G cosine theta. And now I can just factor out my A and then divide by that factor. So this is just A times M1 plus M2 plus 1/2 m sub P equals all of that, which is a common way. We just describe all of that when you're in the middle of a step. And so we end up with our end result of M2G sine theta minus mu sub K M2G cosine theta all over M1 plus M2 plus 1/2 m sub P. Great, and that's our answer. And then if I wanted T1 and T2, I already have them defined here in just terms of A. And so I would just say T1 equals this, where A is that, etc. So that is the end of this problem. Hopefully you see how methodical Newton's second law can be, and that you just combine your equations of motion just like we always have. We just now can also include rotating objects. All right, let me know if you have any questions.